Welcome. My name is Matthew Kerezsi.
I'm James Clem.
And I'm Charlton Becker. Today we're going to be going over a solution to a dynamics problem. First, James will be going over the problem, the free body diagram, the givens, and our approach to the problem. Then I will be going over the first two steps of our solution. And then finally, Matt will wrap it up and go over the final step to our solution. Now I will turn the floor over to James.
So this was the problem we were asked to solve. A flywheel is rigidly attached to a shaft of 1.5 inch radius that can roll along parallel rails as shown. When released from rest, the system rolls 16 feet in 40 seconds. Determine the centroidal radius or gyration of the system. Now here is our generated free body diagram. As you can see, you have mg going down, or normal force acting perpendicular to the rails. You can also see our coordinate system is oriented 15 degrees to be parallel with the rails. Our given data was that it was released from rest, delta x is equal to 16 feet, initial x is equal to 0 feet, change in time is 40 seconds, r is equal to 1.5 inches, which is equal to 0.125 feet, and theta is equal to 15 degrees. Some assumptions we made in approaching this problem was that no friction was between the shaft and parallel rails. Counterclockwise rotation is positive, x is positive in the left direction along the incline, and y is positive in the up direction perpendicular to the incline. So this problem required multiple steps to solve. Since the problem stated release from rest, conservation of energy was thought of at first. However, this would require more steps than necessary, such as solving for the height and equation for Ig. So taking a step back to simple kinematics was a more practical start. I'll now turn the floor to Charlton to go into further detail into our solution.
Alright, now let's go over step one to our solution. The first step to solving this problem was solving for the acceleration. Using the constant acceleration equation given here, and knowing that a is the only unknown to this equation, we were able to solve for a and get 0.02 feet per second squared. Since we solved for acceleration in the last step, we can solve for angular acceleration, alpha, which will be needed in the next equation. Solving for alpha, we get 0.16 radians per second squared.
Final step in solving this equation is solving for raised to gyration k. We use one of the equations for general plane motion. By taking the moment about point C, the point of contact between the axle and the parallel rails, which equals Ig alpha plus MAR. Ig alpha accounts for the rotational movement of the flywheel, and MAR accounts for the translational motion of the flywheel. The x component, the only relevant component for the moment, is sine 15 mg times its distance r. Notice that Ig can substitute to mk squared since we're solving for k, and A substitutes for alpha r as we noticed in the previous step. Also notice that the m's cancel. Factor out the alpha, simplify, and sub in the known values to solve for k. Thus the radius of gyration equals 2.55 feet. This concludes our video solution. I hope you're satisfied with our method. Thank you for your time.